Hello, I'm Brian Young, and today we're going to do 26102, Safety for Electricians. Let's get started. 26102, Safety for Electricians. After successful completion of this module, you should be able to identify electrical hazards and their effects, describe how personal protective equipment reduces the risk of injury, identify the standards that relate to electrical safety, recognize the safety requirements for various electrical hazards. Under supervision, you should be able to properly select and use personal protective equipment, describe the safety requirements for an instructor supplied task, such as replacing lights in your classroom, discuss the work to be performed and the hazards involved. If a ladder is required, perform a visual inspection of the ladder and set it up properly. Ensure that local emergency telephone numbers are either posted or known by you and all other employees, and plan an escape route from the location in the event of an accident. Being an electrician can be a dangerous job. It's important to stay mindful of things that can cause harm and follow basic safety rules. In this module, you'll learn about the dangers of working with electricity. You'll also learn about the types of personal protective equipment used to keep people safe. You'll also learn about the rules related to electrical safety. Finally, you'll learn about the Occupational Safety and Health Administration lockout tagout. Electricity kills. Does everyone know that? More people die on 120 volts than any other voltage because it's the most common in the United States. So don't think that the voltage is what's going to kill you. It's the current. And know that just a little bit of current is enough to kill a human being. And like I say, 120 volts is dangerous as well. Electrical hazards. Identify electrical hazards and their effects. It's critical that you understand what can harm you when doing electrical work. Always be careful and follow all safety rules. Report unsafe activities of your coworkers to your coworkers and supervisors. Safety should be taken very seriously and become a habit. If you remember to be safe, there will be fewer accidents. Remember that you are responsible for your own safety. You have the ultimate responsibility for your own safety. Don't do anything you think is dangerous. 1.1.0, the focus 4. We talked about these before, and if you've taken an OSHA 10 class, then you've studied these. The focus 4, or what are also called the fatal 4, are the 4 highest fatality rates in construction work. Fall hazards, number 1, falling from heights. Electrical hazards, electrical shock, burns from touching energized electrical conductors, caught in between hazards, being crushed by falling material or equipment, or being pinned between a forklift and a loading dock. Struck by hazards, being hit by flying objects or moving equipment such as trucks, forklifts, and other construction equipment. 1.1.1, electrical shock. Electricity is something that causes electrons to move in a conductor. The movement is called electrical current. Metals such as silver, copper, steel, and aluminum are good conductors. The human body is also a good conductor, especially when the skin is wet. As a result, it's important to understand what happens if a person makes contact with an energized surface, as shown in Figure 1. Although it's rare for conduit to be energized, there may be an instance when the conductor's insulation is damaged. If the conductor contacts the conduit wall, the conduit could become energized, and in this situation, the resulting path of electrons can cause serious injury and or stop the heart. So it all depends on what the path the current takes through the body. If it goes from hand to hand and crosses the chest, that's the most dangerous path for electricity to flow through the human body. sure what they're showing. They're showing that there's a short in one of the wires and it's touching the side of the conduit. So the conduit is electrified. The worker didn't know it, and they grabbed onto the pipe and got electrocuted. Actually, it's when they took the pipe apart. They unscrewed the coupling and they pulled the pipe apart. So now the only path for that electricity is to go through the person. Table 1 shows what can happen when electrical current goes through a human body. Look closely at the table. There's only a 100 milliamp difference between a current you can barely feel and one that can kill you. That's 1/10 of 1 amp, 100 milliamps. Milli is 1/1000th, so this is 100 1,000ths of an amp. I've seen these charts before, and there's a lot of discussion about them. Some say as little as 300 milliamps will kill you. Some say as little as 75 milliamps will kill you. I saw one reference material that said as little as 50 milliamps can kill you. And there was one reference material that said if you are above the let go threshold and you get hung up on electricity, you could die in as little as 20 milliamps. If you cannot get off the line, if you're stuck and you can't let go, if it's above your let go threshold, you could die. So as little as 1 milliamp, it's a slight tingling. It doesn't even cause severe pain. 5 milliamps, that's 5/1000ths of an amp. Slight shock that may cause you to react by jumping or falling, which may result in injury. 6 to 38 milliamps is a painful shock which causes you to lose control of your muscles. Somewhere around 18 milliamps is the let go threshold. So we get to the point where we cannot let go of the wire if we grab it. 50 to 150 milliamps, extreme pain and severe muscle contractions which may cause you to stop breathing and possibly die. And 1 amp to 4.3 amps, 1,000 to 4,300 milliamps, dangerous heartbeat pattern, severe muscle cramping, and nerve damage from which you will likely die. Note the unit of measure represented by milliamp, MA, is a milliampere or milliamp. 1 milliamp is equal to 1/1000th of an amp. Electric shocks can also harm you in other ways. For example, electric current entering and exiting your body can leave serious wounds and burns. In cases where burns are under the skin, the injury may not be immediately apparent. OSHA says that if you receive an electrical shock greater than 50 volts DC or 35 volts AC, you need to go to the hospital and have an MRI or a CAT scan. They need to take a look at the injured part of the body. As the electricity flows through your body, it cauterizes the skin, the meat. If it goes through a muscle, there could be a dead spot in that muscle. If too much of the flesh has died, it will not rejuvenate. It'll continue to die, and it can become gangrenous. In a case like that, you'll lose the appendage. You can lose your hand, you can lose your arm, and if not treated promptly enough, you can lose your life. So electricity is a very dangerous thing. We need to respect it, and we need to work safely around it. Always turn the power off. There's no reason to work anything that is energized. Okay. It says over time, however, the skin damage from shock can rot from the inside. Therefore, you should always see a doctor if you receive any kind of serious shock. According to OSHA, electrical-related injuries kill about 350 people every year. That averages out to almost one casualty every day. Remember, if you work in the construction industry, you're at risk of electric shock or burn. There's a warning, it's highlighted. It says, if you see an unsafe condition on a job site, stop working and report it immediately. Your safety and the safety of your coworkers could be at risk if you ignore the hazard. Electrical incidents. It says for 2019 and 2020, non-fatal electrical injuries, over 1,900 non-fatal electrical injuries in 2019. Total electric fatalities is 166, and average medical leave due to electrical injury was 9. Now look, in 2020, we had more non-fatal electrical injuries, but we had fewer fatalities, which is good. And we had fewer lost time accidents. So we're improving in some ways. We have to make sure that we also get this number down. We don't want people becoming complacent with electricity and getting injured. Other findings from the study here, this is highlighted. It says contact with conductors caused 30% of all electrical accidents, with 66% of the accidents involving contact with low voltage conductors, those carrying 1,000 volts or less. There are different ways to talk about low voltage and high voltage. We are inside electricians, so we consider 1,000 volts or less as low voltage. Linemen, outside electrical workers, I think it's anything up to 2,300 volts is considered low voltage, and then 4,160 up to 10,000 volts is considered medium voltage, and anything higher than 10,000 volts is high voltage. So approximately 8% of electrical injuries were fatal. For non-fatal electrical injuries, workers spent an average number of 9 days away from work. Portable handheld electric tools made up the second largest number of injuries. 15%, almost 70% of these injuries happened when the frame of the case of the tool became energized. It had a bad ground. They weren't using a GFCI. Many of the accidents could have been prevented by following electrical safety guidelines and procedures, using properly maintained grounded or double insulated ungrounded tools, or using ground fault circuit interrupter protection. So here's the logo indicating double insulated. They have a tool and then they completely insulate that tool in a plastic shell so that you do not come into contact with any metal parts. That's double insulated. This tool is double insulated, and the plug only needs 2 prongs. It does not have a ground wire. It doesn't need to be grounded. It's double insulated. High voltage, identified in the NEC as more than 1,000 volts, is almost 10 times more likely to kill you than low voltage. However, you'll spend most of your time working with or around lower voltages. So be very careful. 1.1.2, the body and resistance. Electricity travels in closed circuits. A body is shocked when it becomes part of an electrical circuit. This typically happens in one of 3 ways. A person touches 2 conductors at different potentials. A person touches something that is grounded and 1 ungrounded conductor of an electrical circuit, or a person touches something that is grounded and a conductive surface that has become energized because it's touching a live conductor. When this occurs, 3 things can affect how badly someone is shocked: the amount of current flowing through the body, the path the current takes through the body, and how long the body is in the circuit. So if you have an electrical current flowing from fingertip to fingertip, you most likely are not going to expire. You're not going to die from that shock. It'll be painful. You may end up losing the hand. You may end up losing the arm, hopefully not. But if you get a shock on your hand and it enters and exits the same hand, it hasn't crossed this critical portion of your body where your heart is. Likewise, if it comes from one leg and goes down the other leg, you'll probably survive it, depending on the severity of the electrical shock. If it goes from the left leg to the left hand, it's very dangerous, but it's not as dangerous as going from the left leg to the right hand. I know I'm doing that backwards, but you don't want to cross the torso. You don't want to cross where the heart is. And if it goes from arm to arm, that's the most fatal path for current to flow through the human body. It crosses the chest. It can paralyze the lungs. It can stop the heart. The heart can go into what's called ventricular fibrillation. You can die from it. Current must enter the human body at one place and leave at another. Hand-to-hand resistance is 1,000 ohms. So they talk about I equals E over R. The current equals the voltage divided by the resistance. So 50 volts divided by 1,000 ohms is 0.050 amps, or 50 milliamps. And they said 50 milliamps is enough to kill you. So other things can affect shock, including the frequency of the current, what part of the heartbeat is occurring when the shock comes, and how healthy a person is when the shock occurs. Skin is made up of 3 layers. When it comes to the effects of electrical shock, the most important layer is the outer layer. Most of this layer is made up of a protein called keratin. This protein provides most of the body's electrical resistance. When it's dry, the outer layer of skin may have resistance of several thousand ohms. When it's damp, however, or when it gets wet from sweating, the outer layer has much less resistance. If the skin has a cut or scrape, it also results in less resistance. Different people have different levels of resistance. An older person with thick outer skin will have a much higher resistance than a child. Different parts of the body also have different levels of resistance. For example, a worker may have higher resistance in his hands than on the back of his calf. So here they're talking about the heart, and they're talking about ventricular fibrillation. If the body receives an outside electric shock, the heart may stop beating and quiver instead. When this happens, it's called fibrillation, the uncoordinated quivering of the heart muscle caused by an AC electric shock. A heart in fibrillation can't pump blood effectively. In fact, the person can die if either the heart doesn't return to a normal beat. If their heart doesn't. A machine called a defibrillator, like the one shown in Figure 5, is designed to give the heart a shock that restores the heart's normal rhythm. So this is an AED, automatic external defibrillator. This is the one you see on TV where they have paddles. The ones you'd use in the field have sticky pads that you stick to the body, and one goes on the right shoulder and one goes on the left rib cage so that it crosses the path where the heart is, and then it will take the person's pulse and decide if they need an electric shock. And if it detects fibrillation in the heart, it'll say shock warranted, clear the body, don't touch the body, and then push the green button or red button, whichever. You push the button it tells you to push, and it will administer a shock across the person's heart, hopefully restoring a normal heartbeat. Nerves also send electrical impulses to control other muscles in the body. Since nerves also conduct electricity, a person who's shocked can lose control of their muscles. This explains why a person who's being shocked may not be able to let go of a conductor causing the shock. So our central nervous system works on, I've been told or led to believe, 8 milliamps, 8,000ths of an amp. That's what your nerves use to communicate. Your brain communicates with your hands, and it sends a signal to your muscles and tells your muscles to operate. Anything greater than 8 milliamps. In men, they say the let-go threshold is between 15 milliamps and 18 milliamps. Your brain is telling your hand to let go, and the 15 milliamps or greater from the external electrical shock is telling your muscles, hold on tight. And you can't override it. You can't, with your mind, make your hand open up. That's the let-go threshold. That's the point at which you could die from electrical shock because you cannot get away from it. You can't let go. That's what they're talking about there, the let-go threshold. 1.1.3 burns. Burns, the most common type of injury caused by electrical shock. There are 3 types of burns that result from electrical accidents: electrical burns, arc burns, or thermal contact burns. So electrical burns happen when the current flows through the body. The body becomes burned because of the heat made by the current. An arc burn, an electric arc, happens when electric current jumps through the air from one part of the circuit to another, like welding. It's an electrical arc. If you contact any part of this arc, you can get an arc burn. And then a thermal burn, the temperature of an arc between metals can reach up to 35,000 degrees Fahrenheit, which is about 4 times hotter than the surface of the sun. Even if you're several feet away from the arc, you can get a very bad burn. Most electrical safety rules focus solely on shock, so you follow those rules and still get an arc burn. Electric arcs can happen because of bad electrical contact or poor insulation. They can also happen when lots of current flows through a vaporized terminal material like metal or carbon. The heat of the arc depends on the current available from the source at the point of the arc. It also depends on how long it takes the overcurrent protective device to clear or open. For this reason, arcs from low voltage systems can be just as dangerous or even more dangerous than arcs from higher voltage systems. And then they're talking about Ohm's law. We'll learn about Ohm's law later. E divided by R equals I times R equals E. This is the one I like. I equals E divided by R. They didn't give us, here it is, I equals E divided by R. That's the one I like because it tells the true story. Anyway, we'll talk about that when we get to that part. Thermal contact burns. Thermal contact burns can happen when someone touches a hot object thrown during a blast from an electric arc. If you're in the way of a flying piece of molten metal, you may get a thermal contact burn. Why are things thrown through the air when an arc happens? There are two causes. First, the air around the arc becomes very hot, causing pressure to develop. Second, metal expands as it is vaporized. For example, copper can expand more than 67,000 times its original size when vaporized. Once vaporized, particles in the metal can be inhaled. That's a very bad situation to be in. The copper bus, there's a short circuit and the copper bus is exposed to 35,000 degrees Fahrenheit and it goes from a solid to a gas. It becomes gaseous and it expands 67,000 times its size. The percussion of the air exiting that explosion is at 700 miles an hour. You can be 15 feet across the room away from it on a ladder and it can knock the ladder out from underneath you. If you're standing anywhere in the vicinity and you do not have hearing protection, it will burst your eardrums. You'll be deaf. The shrapnel, the liquefied metal copper, can go right through your arc suit and go through you like a shotgun blast. So there are several ways to die from an electrical explosion. It's arc blast, very dangerous. So here they're talking about that. Sound and pressure waves cause hearing loss and can rupture eardrums. Intense light can reach 35,000 degrees Fahrenheit and cause arc flash burns. Shrapnel impairs, lacerates, and causes thermal contact burns. Vaporized copper can be inhaled, burning the mouth, throat, and lungs. That's very bad. And then once it cools, it solidifies, and now you can't breathe. Molten metal sticks to skin and clothing, causing thermal contact burns, and hot air rapidly expands, blowing everything outward. In places other than residential units, Section 110.16 of the National Electrical Code requires that all switchboards, switchgears, panel boards, industrial control panels, meter socket enclosures, and motor control centers be clearly marked to warn qualified persons of potential electrical and arc flash hazards. It's important to remember that qualified persons are different from competent persons. OSHA defines a competent person is someone who can identify current or predictive hazards to other employees and has the authority to take corrective action. Competent persons also have the authority to eliminate hazards through corrective actions. So, what does this say here? It requires a permanent arc flash label be field or factory supplied to service or feeder supplied equipment rated at 1,000 amps. 1.1.4 Electrical Safety Precautions. There are many things you can do to reduce your chances of getting shocked. Always follow your company's safety rules and all other applicable rules and regulations, including job site rules. In addition, Occupational Safety and Health Administration publishes the Code of Federal Regulations 1910. 1910 covers OSHA standards for general industry. 1926 covers OSHA standards for construction industry. Those are highlights. I'm going to highlight that. 1910 is general industry. 1926 is the construction industry. And table 2 shows the minimum safe distance to a fixed energized component. It's based on information provided for AC and National Fire Protection Association 70E standard for electrical safety in the workplace. So 3 feet 6 inches up to 750 volts, 5 feet up to 15 kV, 1000 volts, 6 feet up to 36,000 volts, 8 feet up to 121,000 volts, 10 feet for 145,000 volts, and 11 foot 8 for 169,000 volts. Basically, if you don't know what the voltage is, stay away from it. There are several things you can do to make your job safer. Wear the appropriate personal protective equipment. Remove all conductive items such as jewelry before working on electrical equipment. Work in pairs when working on energized equipment. It's 4 eyes are better than 2. Have someone there who can watch you, you can watch them, and if you're about to do something stupid, they'll say, hey, don't do that. Okay. Understand the hazards and your job well. If you don't understand something, get clarification. Locate possible hazards and shut-off switches prior to starting a project. Also plan an escape route in the event of an emergency. Follow all lockout, tagout procedures or protocols. Know who you need to contact if an emergency does occur. Talk to your supervisor if the job becomes more complicated than originally planned. Always plan ahead and stay alert at all times for potential hazards. This one is very important. I'm not going to highlight it, but it is very important. You know what? I am going to highlight it. Talk to your supervisor if the job becomes more complicated. A lot of accidents happen because of a change in scope. You're going to go take an arc plate, a flash plate off of a panel, and you're just going to determ a number 10 wire on that circuit breaker. When you go to turn the circuit breaker off, you find that it is damaged. It's cracked in half. It's still on the stabs. It's still energized, but that circuit breaker is no good. Stop what you're doing. Put the arc plate, flash plate back on and go talk to your superintendent, your supervisor. Some people think, well, you know what, I saw a spare circuit breaker. We'll just go ahead and change this one out. No, that's when a lot of accidents. I don't know the percentage. I don't want to say 90%. I don't want to say 60%. A lot of jobs, accidents occur because someone didn't. There was a change in scope. You got into the job and you found it's more complicated than you thought, and you didn't just close the patient back up and go talk to your supervisor. That's what you need to do. Close everything back up and go talk to your supervisor. You try to move ahead. You're going to be a hero. I'm going to fix this, and I'm going to show them I know what I'm doing. Someone's going to get hurt. You can't do that. All right. Note, refer to the most recent edition of the National Fire Protection Association 70E, the standard for electrical safety in the workplace, for comprehensive information on safety-related work practices and requirements. 26102, electrical safety. Section 1.2.0, verifying circuits are safe. Note, you must be a qualified person wearing the proper personal protective equipment before you can perform this procedure. And then they go on and talk about a live, dead, live test. I believe that is a highlight. Live, dead, live. You make sure your meter's good by testing it on a known live circuit. Then you test it on the circuit. You want to make sure that it's dead. When it is, you lock it out, tag it out. but you still have to go back to a known live circuit and make sure that the meter is still functioning. It's a dead live test. Make sure the circuit's properly locked out and tagged. Confirm the test instrument is working properly by testing it on an energized item that has a known voltage. You can use a proving unit to perform this task. To use a proving unit, connect the leads to the testing instrument to the positive and negative terminals of the device, then check the test instrument to make sure it's displaying the correct voltage. Step 3, put on the appropriate personal protective equipment. Now using the test instrument, check the circuit you think is dead. The voltage should be 0. Test line to line, line to neutral, and line to ground if present. Step 4, verify the test instrument is still working properly by using it one more time on a known energized source that has a voltage you know. Warning: under all circumstances, always test before touching any electrical conductor, even if it has been locked out and proven to be previously de-energized. 1.3.0 Electrical Incidents and Risk Control. Causes of electrical incidents: unsafe conditions, unsafe equipment, unsafe actions. Safety rules exist to help you identify unsafe equipment and reduce dangerous working conditions. There are also many new technologies and practices that can help reduce electrical incidents. Some of these include proper training for employees and employers, ground fault circuit interrupters, touch-safe terminals, insulated tools. So why do so many electrical accidents keep happening? Most electrical injuries occur because people fail to follow safe work practices or don't recognize a hazard. According to OSHA, some of the most common causes of electrical injuries include failing to make a circuit or piece of equipment safe, touching energized power lines with ladders and powered construction equipment, using powered hand tools, extension cords, receptacle outlets, and installed electrical equipment that lack GFCI protection, working with damaged or worn power cords, including cords with missing ground prongs, operating equipment improperly, which can include making extension cords from multiple receptacle boxes, fabricating extension cords from non-metallic sheet cable, or using power tools with damaged or modified cords. Prevention through design. NIOSH started a national program called Prevention Through Design. The goal of the program is to prevent or reduce on-the-job injuries, illnesses, and deaths by removing the danger before work starts. For example, many power tools are so loud they can damage workers' hearing. All workers must wear equipment to protect their ears. The Prevention Through Design program encourages the use of quieter power tools. 1.3.2 The hierarchy of risk control. So here is the hierarchy of risk control. The very first thing you try to do is eliminate the hazard. Remove the hazard completely. That way it's no longer a hazard. Substitution. Replace the hazard with something less dangerous. Engineering controls. Use barricades, safety nets, guards, and other equipment to isolate the hazard away from people and the environment. Awareness. Staying alert to danger and using warning sounds to alert workers of a hazard. Administrative controls, using rules and regulations that cause people to work safer. And the last line of defense is personal protective equipment, wearing safety gear at all times. Elimination, substitution, and engineering controls are the best way to reduce risk. That's a highlight. Awareness, administrative controls, and personal protective equipment are the least effective ways to reduce risk. Personal protective equipment is the last line of defense. It should not be the first line of defense. 1.0.0 section review. Which the following is true about electrical shock? Most electrical incidents involve touching high voltage conductors. No. Construction workers are no more likely to be electrocuted than other workers. No. CPR can be used to fix heart fibrillation. Most electrical accidents involving handheld power tools occur when the frame or case of the tool is energized. D. That's the correct answer. A live, dead, live test is used to verify that a circuit is de-energized, that a circuit is working properly, whether a motor works, the voltage of a known power source, that a circuit is de-energized. That's the live, dead, live test.